Hello there, friends. I am Daniel De Leon of Group 5. I am going to discuss about context-free language. First, what is a context-free language? A context-free language, or CFL, is a language that is defined by some context-free grammar, or CFG. Basically, a CFL is any language generated by a CFG. The language of a CFG is a set of strings that can be derived from its start variable. Different CFGs can generate the same CFL. So knowing that a CFL can only be generated by a CFG, let's define a CFG. A CFG can be defined as a formal grammar in which every production rule is in the form A derives alpha, where A is a single non-terminal symbol and alpha is a string of terminals, non-terminals, and empty. A CFG can be formally defined as a 4-tuple G is equal to VTPS. V is equal to a set of variables or non-terminals, each of which represents a language. Usually V is denoted by capital letters. T, a set of terminals which are the alphabet of the language being defined. P, a set of productions which has a form variable derives string of variables, terminals, or empty. And S, the start symbol, which is the variable whose language is the one being defined. So, let's proceed to the formal definition of a CFL. Given a CFG, G is equal to VTPS, the language of G is denoted as L of G, where string W is an element of T closure and W can be derived from the start symbol. If G is a CFG, we call L of G a context-free language. Let's have some examples. Example number 1. Given grammar G with variable S, terminals 0 and 1, production P, start symbol S, where P is equal to S produces an empty string and S produces a 0S1 string. Again, let's have a simple derivation. The first production S produces 0S1 right here. Since it's recursive, we can substitute S with 0S1 again, producing 0S11. Since S can substitute with an empty string, because S produces an empty string, the next production will be 0011. Therefore, L of G is equal to 0 raised to n, 1 raised to n, where n is greater or equal to 0. Or right here, L of G accepts a string W with terminals 0, 1, or empty, where the number of zeros and ones are equal. Just by looking at the final production, the final string rather, the given grammar produces or generates a string 0011. So you can see here, the number of zeros and ones are equal. Example number 2. Given a grammar G with the variable S, terminals A and B, production P, start symbol S, where P is equal to S produces ASA and S produces or derives B as B, and S derives empty. So, again, let's have a simple derivation. The first production, S produces A as A. Again, since it's recursive, we substitute S with A is A as A, producing AA as AA. Substitute S with B as B, resulting to AA, B as B, AA. Again, let's substitute S with an empty string, producing AA, BB, AA. Therefore, L of G is equal to A raised to M, B raised to N, where M and N is greater or equal to 1. Or L of G, right here, accepts a string W with terminals A, B, and empty, where the number of A's is twice the number of B's. So just by looking at the generated string of the given grammar, we can immediately observe that the language accepts a string of A and B's, where the number of A's are twice the number of B's. We have 4 A's here and 2 B. So that's all, folks. The end.